Let's do some dynamic pricing with a log-log demand function. This is a second video in a series of 3 videos. The first one was dynamic pricing with a linear demand function. Linear demand functions are easy to use and to analyze, but they're not very realistic. Today we'll look at the log-log demand in this video, and the third video has to do with endogeneity and two-stage least squares. Okay, so just to take a look at different demand functions, the linear demand is the quantity is just a linear function of price. Beta 0 plus beta 1 price, and of course beta 1 would be negative. The log linear is, you say the log quantity, log of demand, is linear in price, and it has a very nice equation for the optimal price. It's just an additive markup. You just take your variable cost or your unit cost and you subtract off 1 over beta 1. Today we will look at the log-log demand, where you take log demand is a linear function of log price, and then you end up with multiplicative markup, where you just take your variable cost or your unit cost and then you multiply it by this factor. You just need the side condition that beta sum 1 is less than minus 1. Okay, so here's just an example to get things rolling. It's a chain of barber's haircut, right? I need to go and get a haircut, but COVID intervened. We have 120 observations of 10 stores over 12 months. So it's panel data. And we have the variables in the data set are the units of haircut, the number of haircuts, per store per week, or is it monthly data. The ad spend, how much did the store spend, the price of the haircut, and then the competitive price, which is the average price at the competition in a local area. Okay, so the log-log demand function can be written as a power function, somewhat related to the Cobb-Douglas production function, but you have the variables all raised to a coefficient, and then you have this strange thing out here, which is just the y-intercept plus an error term. And the reason for writing it like that is if you take the natural logarithms all the way through, you get a linear function, right? So even though as a function of price, this is not linear. Statisticians call it linear because it's linear in the coefficients. Okay, so what you do if you have this kind of data, you have the raw data is things like advertising price, competitor price in units, and here we just take the logarithm. So we just take equal to ln and the cell and just copy and paste it. Once you get a column of numbers, well, you can just put them in any kind of software package and just go ahead and estimate models. This is just a plot. This is just units versus price on the original scale. And you can see that when price is large, the number of units being sold is kind of small. It kind of has a little bit of curvature to the relationship. When price is small, the number of units being sold has considerably more variation. Whereas when we take the log transform, it seems to straighten it out and makes more like a consistent tube all the way through. Okay, and so this is oftentimes a logarithm is called log stabilizing transformation, and one of the assumptions of a regression model is that the variation you see in your data set is constant around the estimated trend line. And on the original scale it isn't, but when you take log transformations it is. So that's a good thing for us, right? That's really helping us when we take the logarithms. Okay, so we can just put it into any kind of software and get an estimated model out. And what we have here is, well, there's the estimated model. If you want to take it back to units, you take the anti-logs, and when you do that you get these exponents up here. Okay, so the coefficient for price in the log-log model is actually the price elasticity, and that's minus 2.484. Okay, all right. And so from that you can get a profit function. And what we have is the unit price minus the unit cost, that's the margin, times the demand. Ad spend goes right off the bottom line, right? It does not depend on how many haircuts you have that week. The ad spend's constant. It's a fixed cost. So you just subtract off the ad spend, and then of course your other fixed cost, right? Now what we do know is that the variable cost of a haircut is $15, right? And given the competitive price, you can use either calculus. You can actually apply calculus to this and solve it, or if you just like to use an optimization package like Solver, you can set it up and solve it there too. All right, so here's just using Solver, and this is price and ad spend, and this is the profitability. And one thing you will notice is that the curvature of this function is a lot larger in the price direction than it is in the ad spend direction, right? So finding the optimal price is easier than finding the optimal ad spend. Now, it doesn't really matter too much, right? If you miss the optimal ad spend, it doesn't have a huge impact. Here we're assuming that the competition price is $25. Just using Solver, we'd find the optimal price is $25.11, a little bit more, and our optimal ad spend in thousands of dollars, $39,000. How many haircuts do we have? We have 14,000, and our profits is $105,000. Okay, and then if we go up to $30, one thing that's kind of interesting, if the competition has a higher price, it doesn't affect our optimal price of $25. We're still going to be using that. But what it does change is our ad spend. Our ad spend goes up, right? So it's almost as though the algorithm says, hey, the competition is charging more. Our price will stay the same, but we'd like to spend a little bit more, maybe attract more business, right? Still more customers. So we have more haircuts and higher profits. And if it goes up to $35, same thing. Our optimal price is $25, but now we're spending more in advertising. Okay. All right. So what you have with the log demand function is that you have the markup. You just have a constant markup, multiplicative markup, where you take the unit cost or the variable cost and multiply it by the coefficient of log price divided by 1 plus the coefficient of log price, right? So that's a pretty simple kind of thing. And in this kind of model we're fitting, the optimal price does not depend on other factors. So that's very simple. So this kind of thing is very simple. If you imagine, I like to call it the Walmart problem, where you have 100,000 SKUs in a superstore and you have to price them all. Well, this kind of model makes it pretty simple. So if you go down and take a category such as detergents, you can just estimate the demand for the different brands of detergents. You know the unit cost, and then you have a markup. Okay, so that makes it pretty simple. All right, what we just computed is called a Nash equilibrium, and it's kind of like saying, hey, what's the best that we can do given what the competition's doing, right? So we have a little bit of competition in this model. We know what the competitive prices are. We have a demand function that depends on the competition, and so we can find out what's our best action if we know what the competition is going to be doing. And there's John Forbes Nash, who won the Nobel Prize in Economics in 1994 for his work in game theory. All right. Okay, so if you know calculus, and you're very fortunate, and you can go ahead and just work out what the optimal price will be if you have this profit function. And so you just take partial derivatives, set them to 0, you find price is, there's the markup, multiplicative markup model, and then if you go ahead and take a look at ad spend, it's a little bit more complex, but you still get a nice equation out. And I check those against what you get in Solver. You get the same answers out. So that's kind of cool that calculus actually works, right? The nice thing about having an analytical form for this is it's a very simple algorithm to introduce into your any kind of platform you have for pricing, and very closed form, very fast, very easy to update, which is way cool. Okay, all right. Okay, so summary. This is one of the most popular demand functions, is log demand functions. If you go into graduate school in economics, you see that a lot. It results in a very simple markup model. Okay, very simple to do. You can use calculus to solve it. Obviously, there's lots of extensions to it you can do. You could put in various interaction terms where you multiply variables together and so on. But again, if you make it very, very complex, then you might have to go and use an optimization package. But that's not too hard to do these days either. Okay, so I hope you got something out of this video, and if you did, please hit like, and I hope to see you in the next video. Okay, so long for now.